So while we are waiting, if anybody has logistics related questions, you could please ask as well. You can just post that on the chat. And in the meantime, I'm just gonna share my screen just to remind everybody where and how we are organizing the class. A majority of the class is organized on the Notion page, so you should all have access to it. I'll add a lot more resources here, and especially PDFs of papers if people can't find those papers that are in. All the recordings show up here. But most importantly, the two most important aspects of this class as a participatory class are these team rosters. If you have not had the chance and you would like to participate and you want to share the sets of details, right now the contact details are via Discord. You can share that. Most mentors have things written about what they're interested in. Also, all the participants at this point, I think, have attendees, have input. If you have not had the chance and would like to, just add your name, Discord ID, and your Notion pages. These Notion pages are your lab notebooks, and it's just, for others, it's absolutely fantastic to just read about what other people are trying to give you the breadth of creativity that's associated with the class. So if you have not had the chance, please try to fill some of this information. This will become very valuable for team building. And then I want to begin officially with one first comment that I wanted to make today was, I'll just stop sharing, I was going through the list of participants, and I think it occurred to me that maybe the first two lectures I didn't emphasize it enough. There is just an incredible talent of people that are engaged in this class. And I think just, I can't even begin to tell you how excited I get about it. So we're all collaborators in this. I identified specific mentors because I wanted to wrangle them into helping me teach this class. But on the other hand, more and more I realize, and you will see an example of this, that the participants, or the collaborators is the word that we are using for everybody that's participating, have worked in fields that are very relevant to what we all care about for many years. And so when you are looking at this class and the team members you're getting a chance to work with, everybody is at a level where everybody is trying to learn, but many people have a lot to contribute in the class itself. And you'll see the example of that today, that one of the participants / collaborators will actually be sharing some of their work from South Africa. So take the time to look through this list. It's a little bit overwhelming, but I think, I don't know how that happened, either accidentally or through word of mouth. We really have a phenomenal group of people. So when you're looking for teammates, which we will talk quite a lot about, keep an eye that you're actually working with people who have engaged in these issues for a long while. So that was the first thing I wanted to say. And then I want to say a word about the idea board that has just absolutely exploded. I'm sure all of you have gotten the chance to see it so far. I'm just going to show that one more time. So on the Notion page, if you have not seen that as yet, please jump to the Notion page at Idea Board. This is how we will structure projects for this class, and this is how we will also do team building. There are many ways of looking at this. You can click here, turn this into a board view. You can turn it into a table. I think the last time I checked, there's something around 150 ideas posted here. And of course, we won't get a chance to work on all of them, but we will be making these ideas and these notes public, so as an output of this class, so others can also work and engage. And ideally, maybe 50 or so of them with team members, we will essentially engage in those. It's very important, and I will emphasize that in some of the design reviews that we will start on Wednesdays and Fridays, which I think we've just described. We will walk through, but it's actually extremely important that when you're looking through these idea boards, try to make them concrete. So I'm just clicking on a random one that I just picked. Can we use invasives to manufacture paper, or can we reduce water consumption in paper manufacturing? So it's a very clean question. So try to make the question clean, but try adding details. If you're interested in that question and you want to recruit other people, you want to be able to add the scope of the problem. So what we will do this week outside the class time is really refine the sets of, and again, lots of them have tons of discussions that are already happening. So, but try to make sure that these, and I'll talk about this offline a little bit on what a good idea board is. It's important to document the sets of discussions. It's perfectly okay for you to be able to change these idea boards as you go along, because it's valuable for it to be the anchor point for the projects. And on the logistics side of this, the proposal is that this week we will all spend time refining these idea boards in a manner that are executable. So I'm looking through the examples for this. You know, for example, how can we feed the hungry planet by 2050? And it's a phenomenal challenge. It maps very well to the sustainability goals. But it's very important that when we are structuring them, that we turn them into executables. And so from the sets of discussions, we start finalizing, and then we rephrase the wordings in a manner that makes it executable in a from a starting point. And this is an art. This is not something that, you know, you learn this along the way of how to chip upon a problem step by step. But that is the heart of the class. And I think it's extremely important for problems and things that you care about, that you try to narrow down such that it's executable, but don't narrow it too much such that there is only one way. And you're now narrowing down the solution space you're working in. So that's all I'm going to say about the idea boards, and the logistics of this will be such that we will have a session on Wednesday and Friday in which we will just explore discussions about these idea boards. This is all asynchronous. People can spend some time. But the goal would be is by around Friday this week, we would have formed teams, roughly the teams between, 5 is a good number. We won't be setting any very specific rules on the size of the team, who you should work with. That is something completely open. But we would be thinking about structuring teams that range from, 3 or 4 to 5 to 6 people. And so if you're interested in an idea, or you thought that what you wrote is very close to what's already on the idea board, propose a merge of those ideas, mention that idea number, this is very similar, and we would like to propose a merge. But if you're just interested in an idea, leave your name there. And I think Tyler will be creating a tag associated with this where will be a property called team. So list your name. And it's actually very important that the purpose of this class is, not to work all alone. It is actually valuable to work together. So try to list yourself in different teams.
Yes, and
okay.
Real quick, I'll
ahead,
clarify
Tyler.
all this. I'll clarify all this via a Discord announcement that'll come right after this. Just basically logistics of how to figure out, where to put what. One quick note: it looks like someone mentioned in the chat that some of the idea board, the ecology biodiversity category, looks like it got destroyed somehow. So first of all, as you're editing this, make sure you're not accidentally deleting things. But I do have an archived copy. I don't know how recent it is. It's probably maybe 48 hours old. So it may have lost some content. So if you've added to any of those ideas during class, I'll be repopulating those, and then you might want to re-add some ideas there.
And then Notion has tracking, so we can look back at it. But please be careful. Idea board is also, it's a precious object, so we should all maintain and take care of it. Okay, so let's transition to, I just want to say a few words about how did people fare on playing with paper. I know many of you have posted on Notion some absolutely remarkable things. And I'm just curious from a context of in the chat, please share certain things. Already there were 2 or 3 properties of paper that I just was absolutely unaware of that have been documented. It's very valuable that all of you got a chance to play. And most of those Notion pages, just from a homework perspective, are all documented right here. So if you go in the Notion page, look in Teams, they are all documented in the team rosters down below. And I'm not going to spend too much time on these, but people should take a look at it. I also just realized that Liz just got online. And since Liz, you weren't there in the first class, we do very brief introduction of mentors. So could you just please do, maybe 5-minute quick intro?
Hey, I'm Liz. Happy to be here. I'm a biology professor. I've been at Stanford for about 23 years. I'm also the faculty director of Jasper Ridge. And Manu and I have kind of been collaborating and thinking about several different projects. Something that I've been really pushing at Jasper Ridge, which is a biological preserve, part of Stanford campus, but just a few miles from the main campus. We're trying to prototype and develop what we call out of the box and into the cloud ideas, where we can sit and develop these things in the field here, but then we can deploy them all over the world. So I have colleagues like now all of you all around the world. My students are people, we've kind of got everyone on most continents, and we're trying to do low cost, accurate, and easy to use kind of technology in order to understand and better sense biodiversity around the world. So whether it's echolocation calls by bats or insect calls by acoustic monitoring, or whether it's looking at the tectonic signatures of earthworms, or whether it's looking at the microbiomes of carnivores using their feces. We want it to be as non-invasive and as easy to use as possible, and we want it to be open source. And how can we detect the biodiversity decline and extinction without better tools that everyone can use? So that's just a very quick synopsis, but basically I'm an Anthropocene scientist, and I'm all about trying to develop and help manage a future that we all want to live in. Thanks, Manu.
Thank you so much, Liz. It's absolutely an honor to be able to engage you. And I think we will do several case studies that are yet to come, where we will really focus on measuring biodiversity as one of the themes of the class, because health and many other challenges, often human health, get a lot of emphasis, lots of people working on it, but I think planetary health often does not get that type of emphasis. So I know many of you are already ecologists and are thinking about this problem, but this is going to be an important part of the, any other mentors that are online? I know Loza just pinged me. Loza, are you online? Could you just do a very brief intro so that we can get started? Tyler, Loza, if you raise your hand electronically, then Tyler will see you. Oh, yeah, you're unmuted. Could you just briefly introduce yourself?
Perfect. Yeah, hello everyone. My name is Loza. I am a 5th-year graduate student at Stanford in bioengineering. Me and my co-founder Tim started an outreach organization called CIFRO, which is Frontiers in Science for the African Continent. And particularly, we've been collaborating with Manu and going back to Ethiopia as a start point to work in university students there. And I think a few of our students and some more are part of this class as well. So I want to say welcome to all of you, and particularly for those joining us from Ethiopia. We are an organization pretty much trying to democratize access to cutting edge science and engineering and all sorts of the inspiration that students deserve to have all over the world. So we're starting in Ethiopia, but our plan is to kind of expand it outward, and sort of this class is kind of the vision for CIFRO. So I'm glad to be part of it, and thank you.
Thanks, Loza. Okay, so we're going to dive into content for today's class. And just as we discussed case studies, the first 5 case studies we will do, we will spend the first lecture on the whimsical side and truly understanding the power of common materials that we see. So we spent a lot of time thinking about paper in the first lecture. And my hope is that you've all realized or believe in this idea that what we take for granted is incredibly powerful as materials that we find on a daily basis. Today's lecture is going to do the flip side of this, which is to say that if this is such a powerful material, have we at a global scale, using the approaches of frugal science, solved any problem at all? Has it mattered for the last 20, 30 years? So the purpose of these 5 case studies is to convince you that these sets of approaches have the capacity to scale. And we're going to spend a little bit of time now sharing in some very specific ways what we learned from the first class, how it got applied, and how it unfolded literally in the last 20 years. So I'm just going to share my screen and so let's begin. And I think, again, a shout out to many people who have done the assignments. I absolutely loved the creativity that was unleashed in the first way. Okay, so let's start with certain sets of applications. Although we will focus quite a lot on detection and diagnostics, I just want to mention a few examples of you can modify and deform and treat paper in ways that gives it superpowers. So one of my favorite examples, and unfortunately I cannot find an actual documented published paper on this, which is a group of Japanese origami artists proposing to release paper airplanes from a space shuttle landing back on Earth. That was a proposed experiment. Nobody got to do it because they were worried if they release it, how will they ever find that paper airplane? But the question was, could paper actually handle re-entry into the atmosphere? And to do that, they treated paper with various properties and I think various coatings, and they were able to get to a point where a piece of paper airplane was able to handle a Mach 7 speed test at 200 degrees Celsius for 10 seconds before it exploded. That's all I've been able to find, but I find this quite remarkable, especially because they realized that ultra-light vehicle might have an easier time entering the atmosphere. The second example I want to give, which is very relevant to what happened in this pandemic, which are many of these filters that are used. So you're seeing that image right in the middle, these filters that are used in ventilators. And there are several sets of origami patterns that are almost essential, because the challenge with filtration is twofold. You have to block something very, very small, and that makes the work of breathing very hard. And that requires a very large area to reduce the total pressure that you would need to be able to breathe through this. And if anybody has been on a ventilator recently or before, the primary tool that protects the ventilator and protects the patients are these filters that you see this picture of. But there is a beautiful piece of work done on origami patterns on these filters to enable high efficiency capture of particles with very large surface area. It's a piece of technology that's hidden behind some of the most sophisticated ventilators is these origami patterns. And it's actually not trivial if you start thinking about building these origami patterns that can be sealed properly. And then the last example I just want to briefly mention is all the way to furniture, which is work from one of the mentors in the class, Zach, which we will talk about at a later time. So paper is used in a very broad range of things in surprising ways. But today's lecture, I really want to focus on truly one example, I believe, that has a tremendous amount of promise, has the capacity to transform human lives in many ways, both in the field of ecological monitoring and human health, and has demonstrated its value, which is really diagnostic technologies built on paper. So I'm going to spend the next 10 minutes telling you an example of a tool that has scaled up, which many of you have possibly even used. across your own lives, and then transition to one of the guest speakers for today, joining us from South Africa, sharing his perspective of the future of what we can do with a simple piece of paper. So, of course, the story sort of begins with, if you have ever wondered and wanted to capture nucleic acids. So there are lots of kits that you can buy. A very common one is called these FDA cards. They are primarily a piece of paper embedded with several reagents that allow for lysis and allow you to capture nucleic acids. One of the challenges that has been for several of these FDA cards, and because several of the technologies behind them are proprietary, is also the cost associated with them. So, you know, it gets us there, but there are several sets of challenges with what you can do with FDA cards. I want to go back to a paper written back in the 1960s. And I love this paper primarily because it at its heart had something very special that it only took 40 years for all of us to actually realize. So of course, you all know, 1944, we discovered that DNA is really the primary sets of molecules. 54, we discovered the structure. But people were starting to work with this molecule, and it was not so trivial, until a group at Princeton decided to look at the binding of DNA to cellulose. And there were several sets of papers in that time, and I could not actually figure out the history of why they thought about cellulose. Maybe they were thinking about the ease of paper itself. And what's beautiful is they demonstrate in these seminal papers, again, from a very fundamental perspective, to demonstrate that you can essentially capture DNA and its hypochromicity, implying the fact that it is being preserved, and especially they were looking at phage DNA, was preserved when bound to cellulose. And that led to a set of a possible technology, which then took a long while to come around and is now being used literally at this very moment. So it's a really worthwhile paper to actually read. And one of the things that, again, going back to what paper actually is, and if you start looking at the hierarchical structures of these cellulose molecules making fibers, they had proposed a very simple binding reaction that allows DNA to both be bound and at that same time be eluted, and several sets of challenges that are associated with elution. This picture on the right also gives you a hint of the puzzle that I had posed last week about, is paper chiral? I'm still not going to, I have not as yet read a perfect answer on this, so I do want you to keep pondering still. But a hint for that assignment is looking at this picture a little more closely. So I think one of the sets that it has led, now you go back and look 40 years later, there's an absolutely beautiful paper that came out in 2017, which really regrouped what was already known to many biochemists, but had been completely lost to many practicing scientists, which is you can actually just use literally toilet paper, many classes of paper for doing nucleic acid purifications. It's a very, very simple assay. And what you're doing is primarily for people who collect samples in the field, but you can also think about diagnosis. And then going back to COVID, you could realize many of the challenges that we have had, both in RNA and DNA extraction, can be solved by a very simple protocol. And I absolutely love this protocol because it is literally something that you can do fairly easily, very simple sets of wash buffers. The proposed is around 30 seconds. It usually takes a couple of minutes for you to do it properly. And what they report is both successful storage of DNA and RNA on these. And essentially the bond is permanent, so you can have multiple washes and still this nucleic acid will remain attached. The other side of the story now is jumping to another piece of technology, which is really at the heart of scale-up of paper from a diagnostics perspective, which is its importance in malaria. So one of the challenges, as you've all heard, is this is an infectious disease that really still takes roughly 500,000 lives every year. So you can imagine it's a very important disease to fight. We also need roughly around 1 billion of more tests to be done for people around the world to tackle malaria. And I want to describe a very simple technology and at its heart of how it actually works that has led to some of the gains that you see literally in that plot. Although something to worry about is you're also seeing that the gains are plateauing now, which is another challenge. At a later time, we will talk about malaria. So I want to introduce you to malaria RDT. It is a malaria rapid diagnostic test. It's a very simple technology, something that you've all probably seen in the context of, say, pregnancy tests. We have all heard about this, and I'm just going to dive in a little bit more detail of what it means and what could we actually do and broaden its access to many other challenges. So to the very right, you're looking at what is called a malaria RDT, and I'm going to take you to a little village in Kalahandi in Orissa. I'm walking into a one-room hospital where malaria diagnosis is happening. And there is Praveen and Durga. Praveen is on the top, Durga is on the right. Durga is running RDT assays, Praveen is running microscopy. These are the two competing technologies for malaria. And at some point of time, Durga is going to get up, and right here, he has just received a tiny drop of blood, and he's essentially adding that to a little piece. He waits for a few minutes. He comes back, makes a reading, writes that in the note, sends the diagnosis out. This is literally happening for hundreds of millions of people around the world every year as a diagnosis test that's happening in the middle of nowhere. And one of the contexts of this, when in 2010, WHO introduced the idea that everybody should be diagnosed before they are treated for malaria, because they were starting to worry about this broad spectrum use of drugs, the fact that that can cause resistance, and also the fact that we were missing out and mistreating many other febrile illnesses, that led to an explosion of both the capacity and use of these RDTs. And frankly, this simple technology can be attributed to a significant decrease in malaria deaths worldwide. And I'll tell you the heart of this technology and the heart of an idea, and especially the simplicity of this idea. But I really think of this from a perspective of the first win as a case study that I want to propose, where very frugal thinking enabled and outcompeted many other technologies that were present previously in malaria. Now, the technology is called lateral flow immunochromatographic assays. If some of you have done ELISA, it's something like that, but done on a piece of paper. So as a homework, what I would like you to do is to go to your grocery stores or Walgreens or medical supplies and try to see if you can get access to a pregnancy test. And as a homework, break it open. And what I would like you to do is document every single component that you see in it in your Notion page. And what you would find is something very simple, which is it's using capillary-based flow to transport the analyte that you're interested in. There are conjugated antibodies, and then there is essentially a test strip with a test location where you're interested in the binding occurring that leads to a chromatographic readout. Now, one of the aspects of this technology that I find very interesting is it was patented in 2002. And interestingly, in 2 years from now, it will be off patent. One of the threads is it's actually worthwhile for some of you, if you're interested in distribution of technology and what it means, you should all read that patent as well. It's quite interesting in terms of how a person thinks about developing a different way of doing something. ELISA had been done for a very long while. But this is one piece of technology that made it accessible very broadly. The other set of tools that had to come along, the paper and doing reactions inside paper was one, but making sure that these reagents and these antibodies would be stable is another. And that has been a tremendous advances on lyophilization. For example, many of these antibodies that are printed are in high sugar concentrations, several protective molecules are added. Some of those are proprietary. So there's a tremendous amount of work to be done to really make a lateral flow assay test a technology platform for others to build upon. It has been a tool that has made a tremendous progress in the field and has made its impact. But I would say it's still not open enough to be a platform for others to design a large number of tests. That is really at the heart of paper microfluidics, which we will talk about in a little bit. So here is the set of challenge. Now you would think that such an important technology with 300 to 500, I mean, literally 500 million tests being done around the world, you would think that we would have developed a distributed pipeline for manufacturing of this technology. And you would be absolutely wrong. This is the other side of the equation, which is although the technology is fairly simple, its manufacturing, its testing, its quality control is still centralized. And I find it shocking when I read many of the papers. This is a policy paper on RDTs. It says, furthermore, since one of the 3 highest volume manufacturers procure major components from one of the 2 manufacturers, 92% of the public sector supply for all malaria RDTs come from 2 manufacturers. One of them is Abbott. Abbott, on the other hand, when it pivoted towards COVID, was using the exact same manufacturing lines that were being used for malaria. And there was a big panic in the world that in 2 to 3 months, we might actually run out of malaria RDTs. So this is what is also wrong when you think about, of course, Frugal Science scaled, but this is our challenge. Unless we provide the capacity for local manufacturing and capacity for hundreds of countries around the world to be able to make essential technologies, we would box ourselves in these challenges where we would not be able to track when supply chains are challenged. The other side of this technology, which is challenging, is unfortunately, because it was used so widely, it led to a resistant strain of malaria, which had a gene deletion in the exact gene that this was trying to detect. And hence, there are several countries now that have this HRP2 and HRP3 genes that have been deleted. So in the end, there is, I mean, it requires us to then multiplex these sets of RDTs. It also allows us to think about that if you globally implement something, the biology will adapt, which is also another sets of challenges. So with that, I am going to transition. I just mentioned to you 2 examples of where paper has literally, I mean, I do believe in the case of malaria RDT, it has changed the world in how a single idea scaled up to an extent that it has supported literally hundreds and hundreds of millions of tests that have been done. Now, I want to look towards the future a little bit. And from that perspective, I actually only recently learned that Kevin Land is one of the participants in the class, and he literally wrote a textbook on paper diagnostics. And Kevin happens to be joining us from South Africa. And I want him to spend half an hour sharing both his perspective from South Africa, where he sits and sees many of these problems directly, sharing the sets of technologies that are yet to come, and also just sharing his passion for this work. So Kevin, are you online? Can you raise your hand? And Tyler, can you unmute Kevin? And then Kevin, okay, Kevin, can you hear us?
I can hear you. Can you hear me?
So thank you for joining us in the evening, Kevin. Maybe you could do a brief intro to yourself, and then let me know if you would like me to share the slides, or would it be better if you share your screen?
Can you see my screen now?
Yes, we can see your screen.
All right, then I'll do the screen sharing from my side.
Yes. Welcome, Kevin.
No, fantastic. Thanks so much for the opportunity, Manu. I first met Manu, I think it was around about 2006, 2007, when he was finishing off his PhD. I think I've got roughly that.
Yeah,
that
I was a
timing
young
correct.
graduate student at that time.
And I remember well that you published a paper on bubble
Yes.
logic, which is still quite worthwhile giving it a read for anybody that would like to. So I'm based in South Africa. I've spent a lot of my time at a science council in South Africa, but I'm currently mostly on my own as an independent consultant currently. And then I also have an affiliated position with the University of Pretoria. So I've spent quite a lot of time originally looking at, I've spent quite a lot of time originally looking at microsystems technologies and micro manufacturing technologies. And I came out of a laser-based photonics environment. So I did a lot of micro machining using laser-based equipment. And then over the last probably 12 or 13 years, I got involved with microfluidics in general. And then I actually did, you know, when I was quite a lot older than normal, I did a PhD in microfluidic engineering. And then use that to really get into diagnostics. And my real interest is in how do we design and manufacture diagnostics for implementation in really low resource areas, which I think is really, really critical going forward. And Manu has already given a really, really good introduction in terms of why that's important. And you'll see in my presentation, a lot of what I talk about is diagnostics. It is for human health. And it is paper-based. Having said that, a lot of those things that I've just mentioned can be substituted. When I talk about human health, almost everything I talk about is also relevant to animal health. It's also relevant to the environment, for example, designing water sensors or something like that. And when I talk about paper, even as part of a lateral flow test, sometimes one's using materials that are not paper. Mm-hmm. And that's also important to take note of. Sometimes, for instance, when you want to get low cost or affordable tests, then you may need to move away from paper because of different functionalities which are given to you by plastics, as an example. So we're not stuck to paper, although paper is an amazing material. And I would say that wherever possible, one would use paper and then only fall back on other materials when really needed, and where paper doesn't give that functionality.
And I think, yeah, there is a beautiful discussion that's also happening on chat on reducing the environmental footprint of many of these sensors if you deploy them in front. All RDTs, for example, use plastic as a covering, and thinking about an alternative to that. But on the other hand, from a functionality perspective, this is why I want all of you to open up the pregnancy tests that you buy. You will find many materials in there, and the core would be paper. Back to you, Kevin.
Sure. Okay. So to get going with the presentation, at some stage,
yeah. So I think, Kevin, think about maybe something like 30 minutes.
Sure.
Yeah.
Not a problem.
Yeah.
So when I was thinking about this presentation, I was actually going to give you a whole rundown of exactly what is in a malaria test, but Manu has given that as a project for everyone to do. So I'll probably mention some of the components and then leave some of them for everyone else. I don't know if, can you see my camera as well if I show it like this?
Yeah.
So I've actually got on my desk, I've got a malaria test, which I, for different reasons, I actually pulled apart around about a week ago. And I also have a clear blue digital pregnancy test. Also really interesting in terms of the digital pregnancy tests to actually look at how they read the test and the control line. And that's also something, if you can get your hands on a digital test, it would also be really good to have a look at how simply and at relatively low cost they actually give you a digital readout of the result. So I'm going to start just by introducing very, very quickly, setting the scene. And I'm going to do that just by talking about one or two diseases or one or two applications. So the first one being HIV. And you may know that the United Nations has the 90-90-90 global HIV target to be met by 2030. And you can read it for yourself, but the first target is 90% of people living with HIV know their HIV status. So currently there are around about 36 to 40 million people living with HIV, and only 60% know their status. And the only way really to get people to know their status is to be able to have a really low cost test, diagnostic test. And there are already HIV lateral flow tests available. So to an extent, part of that needs to be being able to manufacture those to a much higher volume and then to be able to distribute them and read the results where required. And then the third target is 90% of those people actually have a suppressed viral load. And in order to determine that, one also needs to have some sort of a diagnostic. So as an idea, within Africa, there are around about 150 million HIV rapid tests that are done every year. Then in terms of water, so the main risk to communities does lie in bacterial diseases, and that's cholera, typhoid. E. coli is quite a big problem with drinking water. And obviously there are a lot of tests which are available. And there are some tests which are low cost, but it's very difficult to distribute them. Or there are tests which are way more expensive, like the CholiAlert test, but it's not a rapid test, and it is very expensive to actually do. And when I say not rapid, I think the results from CholiAlert, you can get them within roughly 24 to 48 hours. So it's also not useful at the point of need. Tests for rapid E. coli detection. I'm not aware that any of them have actually been commercialized as yet. So these are things, and then just lastly as well, I've talked about the environmental aspects and HIV. Obviously, malaria and TB are also still massive needs, especially within low and middle income countries. And if I refer to that again, I'll refer to LMICs. So the environment in which typically, if you look at this pyramid, typically, and this would be in high income countries, you would, when you go to a clinic or to a hospital, you would be on tier 3 or 4, as shown here. And if you look at that, these are all the different pieces of equipment that you have. And it's all laboratory based, it's immunoassays, it's these nucleic acid tests, it's all equipment based, very expensive tests. As you go down the pyramid and you get towards levels 0 and 1, you have primary care, which are healthcare workers, and then you have the community health workers. And the only tests that they really have access to are these rapid diagnostic tests. And again, showing just the importance of being able to do these tests. So if we look at the 3 A's of diagnostics, and these are quite commonly known, it's quite interesting to think about when you're in, let's say, tier 4, which I showed you, on national level, most people would say that the number one important criteria is the accuracy of the test. So when you go for a blood test or any diagnostic for that matter to your local hospital and you see your GP, you want to know that if you've left a blood sample, the test result that comes back is accurate. And you may not even know how accurate it is, but you're assuming that that's 100% accurate, basically. The affordability of the test is not always of high importance to you because you may be on a medical plan or some other health plan that actually pays for the test, and you may not even know what that test costs. Accessibility is also not that important to you because the doctor or the medical facility is easily accessible to you. As you move towards the 0 and 1 tiers of that pyramid, suddenly, well, not that suddenly, but the accuracy of the test is not as important anymore as the affordability and the accessibility of the test. And this is something which I'll talk about in a little bit more detail later as a possible challenge that we can think about as part of this Frugal Science series. So just to bring in some things that are happening right now, you may know about the X Prize, and that's been run for COVID testing, where they're looking at frequent, fast, cheap, and easy tests. Now, obviously, with the COVID pandemic, there's been a lot of talk about diagnostic tests. And one thing which I think has become apparent to everyone that's involved in some way is that the current testing using PCR, although it's still seen as the gold standard, it also has a lot of downsides to it. And these we can discuss in more detail later if need be. But one of the things, especially in LMICs, is that it's very, very difficult to access the reagents that are required for PCR testing, with the result that not enough testing gets done. And the only way around that, at least in my view, is to be able to develop really, really cheap and easy to use tests. So I'd encourage you to go and look up more about the X Prize. And then I'd also encourage you to go to the FIND website. FIND is the Foundation for Innovative New Diagnostics. And just have a look at the different actions that they're taking as well. And part of the FIND criteria, you will see, I think it's on this web page, they put out an expression of interest, and you could apply to be a manufacturer or provide tests. And one of the criteria is to be able to scale the manufacture of the test. And the other really important criteria was the ability to localize manufacture, or at least share manufacture within LMICs. And that was something that Manu also touched on now, in terms of why can't we actually manufacture more of these tests where they are needed? Why do they all need to be centralized in 1 or 2 countries? And with that, I want to introduce you to this criteria. And it's something that I found very, very useful myself. The assured criteria, so leaving off the R and the E at the top here, the assured criteria was something that the WHO published in, I think it was around about 2007, looking at those specific criteria. And I'll go through them one by one because I think they're really important. And every time you sit with a test and start looking at developing it, I think it's a really, really good idea to sit with these criteria and go through each one of them and see that you understand with the test that you're trying to develop whether each one of these criteria will in some way be addressed. And obviously the gold standard would be that you address every one of these criteria, but that may not always be possible. And then recently, so one of the original authors of that paper was Rosanna Peeling. And I got together with her a couple of years ago, and we looked to assess the assured criteria and see whether, 13, 14 years later, these criteria were still valid. And we basically, we came up with many, many arguments for and against, and we went through the whole process. And we eventually came to the conclusion that the assured criteria are still as valid as they ever were, although there are some new things which could be added. And I think one of the most important was eventually what we called real-time connectivity, but it really refers to the use of technologies which are now available, which weren't available 14 or 15 years ago. And I'll get to some of those a little bit later as well. But I really would encourage you to go and have a look at this paper and just see the criteria and why they're so important in LMIC context. So here, I'm going to go through each one of these really quickly. And I think in terms of frugal science, also think about, when one talks, for instance, about cost, when you're talking about frugal science, ideally, you're wanting to create something as low cost as possible. But at the same time, the only way to get to low cost as possible is to be using technologies to a large extent which are already well developed and where there are already mass fabrication processes. So think about that as we go along. So when we talk about affordable or low cost, do we even really know what that means? And I think it's good to put specific targets on that. So as far as the malaria test is concerned, the WHO criteria for that is a test which costs 25 US cents. And again, when you're pulling that test apart during the week and you're actually having a look at all those, everything that's there, list all those components. I'm guessing off the top of my head, but I think you're going to get to around about 20 to 22 different components in the test. And maybe next week we can talk about it again, is how do you get down to a price point of 25 US cents per test with so many components? And then these other criteria, like an HIV test, for instance, rapid test would be of the order of $1 US. And many of the molecular tests, the target price is around about $10 US. So if one looks at, for instance, the Gene Expert from Cepheid, that would be around about $10 per test.
And I think, Kevin, on the point that you said about multi-component, I forgot to mention, but on the idea board, I'll add an idea board on robotics that's used to assemble many of these. And this is also one of the reasons why manufacturing is not widely available. The fact that I think while we're thinking about components, how these components are assembled is an important criteria.
Yeah, absolutely. I think there are certain volume constraints with, for instance, in South Africa, some of the test manufacturers still do quite a lot of manual assembly, and that's doable up to maybe somewhere in the order of 5 million tests a year, I would guess. But anything higher than that, you need to start looking at massively automating the process. And we can talk about that as well. I know quite a lot about the automation process for lateral flow as well.
Yeah, and I think we'll definitely add an idea board on that, Kevin. Yeah.
Yeah, sure. Then obviously the next two, the two S's, and that's sensitivity and specificity, are really, really important. And I will get to that. I've got a slide which, as I said, I'd like also to possibly be an idea board topic. So I won't talk about it too much. And I think everyone's fairly much aware of the importance of the sensitivity and specificity. And I think there have been quite a lot of articles written specifically now with regards to COVID that people can look up and see what the meaning of sensitivity and specificity really are, in terms of what does it mean if your false negatives are too high, and what does it mean if false positives are too high. Yeah, and can one get away with, let's say, relatively high false negatives if your specificity is really good, etc. So there's also, again, there are a lot of talking points. Some very interesting articles have been written by a guy, and I forget where he's from. Yeah, Manu, you probably know, Michael Mina. So
yeah,
if you'd like to look him up, yeah. So I was just going to say, he's written some really, really interesting articles that give a lot of food for thought about what is required in terms of testing. And if you can, a lot of it's got to do with what is the prevalence, of the disease in the population. And then these concepts have different meanings. So worthwhile also giving it a read for both of these. Okay. Then in terms of ease of use, how many steps does it take to actually perform the test and get to a result? At the moment, for instance, sample preparation is quite a tricky process. And even if you're using PCR or other molecular methods, to prepare the sample, one has to give a lot of thought to. Samples such as blood, for instance, are really easy. So you get a pinprick of blood and you can essentially pipette it directly onto the lateral flow test, as they do with many of these tests. Urine, I think, also a really easy sample to use. But when you start looking at the samples that are being used, even now with COVID, where it's saliva or nasopharyngeal or oropharyngeal samples, specifically with something like TB, where it's a sputum sample, sample preparation is sometimes very, very complex and actually adds a lot of complexity. And that's not always a good thing when you're going to LMICs where you may not have the level of training or skill required. Okay, in terms of time to test, if you look at TB, for example, when TB samples needed to be cultured, that could be up to 2 weeks before you could get a result. Obviously now with the GeneXpert Cepheid test, it's around about 2 hours to a result, which is a massive improvement. But 2 hours on a single instrument still means that you can only do 4 tests per day, which is certainly not sufficient. Now, obviously, you can put these machines in parallel, and many of these machines come with, for instance, 4 sample bays or even bigger. But again, if you can get your sample time down to 15 minutes or even less, as you can with many lateral flow tests, that's a huge advantage. And we know even with the COVID pandemic, a lot of the PCR tests which were done, the samples could be taken, but you didn't get a result for sometimes up to 10 days. I know in South Africa it went even longer than that. In the US, I think sometimes it was several days. And after a day or two, there's no real point in even, for clinical use, for actually evaluating the sample anymore. So the quicker you can get it, the better. Then obviously tests must survive through a harsh supply chain and storage conditions. And then you want something that's largely equipment free as far as possible. Many environments within LMICs don't have electricity, don't have a clean environment, and maintenance can be an issue. Yeah, and then consider the environment where the test is used. So this is something I want to throw out there for everyone to think about, and I don't want to talk about it too much. This is just one possible way of evaluating, and I've drawn up this table as I have just to make it very easy to understand. And obviously there are many, many variables to be considered, like cost, specificity, etc. But if you look at a table like this, let's say that the sensitivity of the test is 100%. So it's a perfect test in terms of you're not getting any false negatives, right? But you can only 30% of the population that needs to take the test actually has access to the test. So in a very simplistic method, we score that at 30. So a 1 times a 0.3 would give you a 30%. If your sensitivity is 90%, which for many tests is not that bad. In fact, the WHO specification for a antigen rapid test for COVID is greater than 80%. But you can access 90% of the population. You score considerably higher. Now, this is very simplistic and open to a lot of judgment, but I think it's something really worthwhile thinking about in terms of if you can, for instance, with COVID, if you can give everybody 2 tests a week, or you can give them a much more expensive test and not access as many people, and once a month, which of the 2 gives you the more valuable information and more valuable way of actually stopping the disease spread? Okay, so Manu, how's my time looking?
Sorry, you have 10 more minutes.
Fantastic.
Yeah, but I think this was absolutely brilliant, Kevin. I think stating the problem well is far more important, because now many of the technological things people will be able to gobble up with the list of papers that we will write. So that was fantastic. And I would say with the access to sensitivity, let's definitely make that an idea board. It would be incredibly valuable for many of the applied mathematicians in the group. It would be fantastic to really do this from a context of a very quantitative measure, because I think many times the way pricing of diagnostic is done is based on what the market is willing to pay for and not based on can we stop a disease. So just absolutely fantastic, Kevin.
All right, then to go on to some of the other work that I was involved in. When one starts thinking about then how do you actually get to a point where you can, let's say, have this reassured criteria, you need to look at what is already there, for instance, lateral flow devices, and I'll show this on the right-hand side here. So we already know that these tests conform to certain of the assured criteria. They're affordable. Many of them are very specific. Sensitivity sometimes lacks. They're very user-friendly typically. They are obviously equipment free and they're deliverable to end users, but they do have some performance issues. So can we then combine them with more expensive technologies? And this is an example just of a cartridge-based microfluidic system, but this could be replaced with PCR or some other amplification method like LAMP or RPA. Anything that you can think about that's done, let's say, in a laboratory with expensive equipment. Is there a way to combine that technology with this low-cost technology? And this diagram here just kind of gives a schematic of possible things to think about. I won't discuss that in detail. I also won't discuss this in detail, but you can have a look at all the different things which we can look at combining onto a single piece of paper. So if one looks at power, for instance, can we, for instance, print batteries? And if one's looking at a low-cost device, let's say would you be able to print a battery for 10 US cents? And that battery, all it needs to do is give you a little bit of power. So it doesn't, it doesn't need a huge output. It doesn't need to last for long. It can last for maybe 1 minute or something like that. Can we print a battery with those criteria, for instance? Can we print, actually, let me move on because I'm going to repeat myself. But you can look at this in more detail later. So in terms of paper-based diagnostics, this is the lateral flow test that Manu spoke about. This is more conventional, what's called micropads, paper analytical devices that was developed at, well, started, let's say, at the Whitesides lab, but now there are hundreds of groups across the world looking at developing these. And you can read all of these things in more detail later, or you can look at these publications. In terms of printed functionality, this is something that I'm still actively involved with, and which I think will importance for the future. There are already people that, for instance, are printing RFID tags for close to 2 US cents per tag onto devices. And if one can pivot that to low-cost environments, that would also be really, really fantastic. And there are groups looking at printing light sources. There's some passive fluidic outputs, readouts. For instance, there's these near-field communication tags, pressure sensors, you name it, in terms of printed functionality. And again, what I want to emphasize here is what I see as really important is there are a lot of big players developing these technologies. So whether it be Samsung or whoever it is, they're developing these printed technologies for their own, let's say, high margin devices. Can we pivot those technologies to what we want to use for very low cost? And keeping in mind that you're looking at your substrate materials are either these sort of polycarbonate type materials or paper, so very low cost. And all the manufacturing methods are already very, very well known. So it's printing technologies which can be inkjet or reel-to-reel, even sheet processing technologies. If you can put a ream of paper in your printer, for instance, and just let it print 10,000 tests, and an hour later you've got 10,000 tests that have just printed on your desktop. Can we get to that point? Then in terms of readers, now I think fairly obviously it would be great to get away with not having a reader at all. And most of these lateral flow tests have some sort of colorimetric output, so you can read by eye. But there is some chance of misinterpretation by eye, and a reader does sometimes also give you more sensitivity. And so you can look at a lower detection limit, and it can also then read some other outputs, whether it's, say, fluorescence or luminescence or something like that. So it's maybe useful to think about, and this is a project that I've been working on, can one use conventional technologies like, for instance, paper box folding and printing of the electronic components and then obviously information? Can one do that and then read lateral flow strips, for instance? And if you need to replace it after 20 reads because it's got damage or something like that, it's fine. You could throw it away, take another one out of the drawer. What that means is that you don't have all the maintenance issues going forward. So that's just a picture of it in some of the tests that were done. Okay, this is getting back to the manufacturing aspect, and I've touched on that. So we already know a lot of the manufacturing methods. The one thing I didn't talk about is screen printing. So screen printing can also be scaled very nicely. And then I just put this here. It was something that I drew up some time ago for a printed electronics roadmap. But I think also I'm not showing it for the level of detail. The main reason I'm showing it is that we often judge things based on their technology readiness level. And I know where I was, the TRLs were, everyone asked you, are you at a TRL 4 or you're TRL 6, or you're ready to commercialize? And everyone would sort of write down on a document, yeah, we're at TRL 6, without necessarily knowing quite what it means. And within the TRL levels, if you go and read the documents, there is something called the manufacturing readiness as well, although it doesn't really have a level. And what I think is really, really important conceptually is to look, when you go up the technology readiness level, so you've proved it in a lab and it works, right? So you're at, say, a 7. try and look at how far you are along the manufacturing readiness level. If Manu comes to you tomorrow and says, you know, within a year, can we manufacturing 10 million of these or 100 million? You know, would you be able to say, yes, I understand the manufacturing methods, I know who to go to, I know what the costing, roughly what the costing would be, etc. And I think that's one area that we seldom really think about, especially if we come out of a, let's say, a technology environment, because the technology excites us and somebody else can manufacture. And I think it's really important to think that to a large extent, someone else can't manufacture it if we haven't thought about that from the start. You know, and that's got to do with, you know, design thinking and, you know, those things, which I think we'll deal with as well.
So I want to reiterate what you said, Kevin. I think for this
that's
class, it's extremely important what you said, that you don't do manufacturing after you have an idea. You really, it's embedded in the host of an idea. And I think the spirit of Frugal Science is that you're thinking about scale. So that table and weeding out ideas that you cannot imagine as yet that have any applicable manufacturing technologies, and choosing something that directly matches this manufacturing readiness, even before you have put anything on a piece of paper, or even if you've built a prototype, I think is a very relevant point. And I feel this is at the heart of why we have hundreds and thousands of publications on all of this is possible, but nothing makes it to the world, is because the training for manufacturing readiness is very limited, and there is siloed in industry, while many people developing these tests just have never been exposed to manufacturing.
Yeah, so I think, you know, one thing that I often think about is what, you know, it's obviously an advantage to have some sort of an engineering way of thinking and a scientific way of thinking. But it's not common that you find that within single people, if you like. So it's really important, again, to look at having groups which are multidisciplinary, and not only multidisciplinary within, let's say, the sciences, but then going across to the engineering side, where you can bring in people that do understand manufacturing and things like that. And it's not only what they understand; it's also, can you talk each other's language? Because often you sit in a room and the scientist goes on talking about certain things, and you know, half the people switch off until it's their turn to talk. So it's really important that people also learn to talk each other's language.
Okay, so I think, do you want to show Kevin, you want to show your last slide? And then we're going to transition. I was just curious where that picture was from.
It's a clinic somewhere in Gauteng in South Africa, as far as I know.
Mm-hmm. Yeah, and I think what I like about what you touched upon is, you know, human health is only one part where this technology has primarily been used so far, but its impact in environmental monitoring, animal health, you know, to be able to detect all kinds of challenges in supply chain of pharmacy, water supplies. I mean, that's the tip of the iceberg in terms of where I really see very large scale implementation. So if you unshare your screen, Kevin, I'm going to open it up for any questions/discussions. I think there was something that Liz had set up that would be very valuable to touch upon as well, which is, in disease, we often think about yes, no, in a single point assay, while if we are doing ecological monitoring and biodiversity monitoring, it's a much more complex signature that we are reading. And that's why I had differentiated the two pivots of nucleic acid capturing technologies can then be read out completely differently in a centralized manner, where your readout could be much more multiplex. But Kevin, I'm just curious, in the paper space, what is the multiplex nature that you have seen so far? I mean, are there sets of things that are being implemented on arrays? I'm thinking about just like our displays, except the display has a really multifactorial readout or an answer.
Yeah, so there are a number of interesting things, I think, which are happening with paper-based fluidics. What, you know, in the lateral flow domain, there are some technologies coming closer and closer, which are multiplexed either in terms of looking for different antigens. And you know, the malaria test is one such example where you may have now 3 lines or 4 lines on a malaria test. So that part of multiplexing. Then there are quite a lot of, and I'm not sure whether these are really commercially available as yet, but there are quite a few people looking at semi-quantitative outputs. And so that's how dark it gets. The problem with many of those is it's almost impossible to, without equipment. So you need some sort of a reading ability. So there are there are a lot of lateral flow handheld readers which do give you semi-quantitative information. And I think the idea is really to see how useful that semi-quantitative information is. And then in the, let's say, the paper-based diagnostics space, there are quite a lot of people looking at different arrays, you know, where you wax print a whole lot of arrays, or you even have some sort of paper readouts. You know, there was one example in my presentation, and there are quite a few groups that are looking at increasing the functionality on paper tests, and that could be on the readout side. It's also on the timing side. So one of the important things is, you know, a lot of these lateral flow tests, you need to read it at say 15 minutes or 20 minutes. And most of the developers say after 30 minutes, you should not read it anymore, because there can be some issues. And so if you can have automated timing on the paper, it's also, you know, a real advantage. So there are a lot of groups working on this. How many of them are getting towards commercial, I'm not really sure. Just about all the commercial stuff really is with lateral flow.
And I think I want to emphasize this other point that you had made about, I was very excited when flex electronics kind of took off. I was thinking it's going to solve all the problems, and I was deeply disappointed that in the end, it is about high margin, what I can wear, the Fitbits of the, I mean, it's valuable and eventually it'll make it, but several technology companies in that space pivoted significantly away from global health, away from environmental monitoring, really about perception of just us as human. We are very human-centered, unfortunately. And of course, it's that's challenging. And I think so the purpose of this class is not just about coming up with new ideas, but taking these ideas and re-envisioning them so that they become more available. So as many of you are thinking about idea boards, don't just think about what it takes to get to the first idea point, but what does it take for the types of general purpose printers Kevin is talking about. Or I want to show one example of what does it take to essentially robotically manufacture, say, 10,000 of these in a place so that people can get to a point where you could do medium scale manufacturing locally. Or for example, the ideas around the antibodies. That is a huge field, but are there ways and means of getting local production of antibodies, for example, which used to be the case for many places. So I think there is this balance, and it would be very valuable that we post a few idea boards, both re-envisioning these technologies and asking ourselves, can manufacturing be much more openly available? I'm just going to show a quick video of this essentially a robot that's general purpose robot for lateral flow assay printing. It's a very short video, but you can, some of the roboticists in this group would think about, you know, these are fairly, I mean, these are sophisticated tools, but it's actually interesting to think about what does it take to assemble. And I'll just shut up. I'll just do this as just a quick 1-minute video.
The solution is easily adaptable and can assemble different rapid tests with minimal product-specific adjustments. Built on Genelys's Xanthia platform, the modular design provides speed, accuracy, and precision, as well as flexibility for the future. The LFDA's bulk feeders are not product-specific and fit a wide variety of cassette types. The lateral flow test strip is fed with single card magazine or reel in-feed modules. The test strip is cut with a linear.
So you see my point. You can all watch this, but many of my friends who get excited about 3D printers and other things, I kind of feel these sets of technologies that just a little more, more degrees of freedom, it would be phenomenal for us to be assembling. I'm not aware of any open source LFA assembly machine so far, for example. And it sets this example where, yes, we can invent sets of technologies, but could we democratize manufacturing in a manner? And could we enable quality control, which is another huge aspect, which Kevin didn't mention, but quality control is really one of the reasons why very large players are the ones that really have the bulk of the share. And how do we make sure? I don't know, Kevin, if you have any comment to make on the QC side of this, because the RDTs and lateral flow assays are really criticized that you have this box, you have no idea when it basically got bad. And so doing tests internally as well. I don't know if in any of those areas or WHO discussions that has been, I know the standards around it.
Yeah, I mean, can you still hear me?
Yes.
Yeah. Yeah, there's a lot of discussion about the quality aspect, and it is, I mean, I think the two main criteria that you look at first is performance and then quality control, because batch to batch consistency and everything obviously has to be really good. So any manufacturer that wants to manufacture these has to be ISO 13485 compliant. And then there are some other criteria as well. So from the WHO perspective, for instance, they need to also get a WHO pre-qualification and things like that. So it is really, really critical going forward. So it's also something to think about is how does one, you know, is it also a criteria that one can add to that good enough, or is it not? Is quality something that always has to be at a certain standard?
And then, Kevin, that comment, I wanted to make a little more political. And I don't know if some of other folks who have experience in this idea of, you know, the certification bodies and, you know, certain sets of technologies and testing and processes can be just bottled up and be hidden. And hence, many manufacturers might not be able to meet the criteria because, I mean, look at the ISO standards that are used for medical equipment. You have to pay tens of thousands of dollars to just buy the standards. So what are the kinds of barriers and what is the politics of this? Because we are talking about, you know, billion-dollar markets. So I don't know, being in South Africa and kind of at the edge between these two worlds, I'm just curious, have you run across the politics of manufacturing in this space? You can also, you don't have to comment, but I'm just putting you on the spot on that side. You know, what happens behind the scenes in these large scale situations?
It is quite difficult to answer because I think within South African environment, I think most of the procurement, large scale procurement is done from international suppliers, not from local suppliers. So they would already have their, you know, pre-qualification and ISO certification done. And then, you know, if it's HIV or malaria or something like that, you know, it's purchased through different programs through the Department of Health or whatever it is. And I think the aid agencies also play a large role in bringing down cost, you know, but then also getting it from specific suppliers. So something like GeneXpert and Cepheid, for instance, when I mentioned the $10 price target, that's certainly not what you pay per test in the US, but that is the price point at which South Africa can buy those tests. But I would think there is a fair amount of, I guess politics is the correct word, but things over which we have very little control. You know, I guess it's also something to think about. What are the things that we can control, and what are the things that we can't control or have any influence over, really?
Yeah, I think it's a very important point because, and only recently, I will share a few sets of references, and one of the mentors, Madhu, and we'll bring him on board, he will talk quite a lot about it, which is the politics of global health and how centers of power have been for centralized for such a long time, and especially in philanthropies itself, although there is good, there is centralization of power in global health. So I think this would be a topic that we'll pick up, and I think it would be valuable for Kevin, for you to contribute in that as well. I'll share a few papers on that front. I already see it's 1:50. That sort of is the official time when the class ends. Usually, it would be phenomenal if anybody wants to stay. Anybody has questions. I don't know, Kevin, if you have a few more minutes you want to stay, I'll stay online for a few more minutes. Any other mentors who wants to stay? We will open the floor to just general discussion, but that is the end of the class. Thank you for coming for lecture 3. I have to say I'm personally enjoying this quite a lot. So hopefully some of you are getting value out of it. We will post all the recordings online and also on YouTube so people get a chance to see. And then you will see an email from Tyler about design reviews, which will be just open-ended discussions on the idea boards, because we really have to narrow. For us to achieve something in this class in a short period of time, we have to narrow and hone in the craft of going from an idea like what Kevin shared to really something that's concrete that somebody will act upon. And that is what we will talk about in the design reviews on Wednesdays and Friday. We chose a time that is convenient to, one time that's convenient, or we thought was convenient to the time in India, and another time that's convenient to time in the US. But with that, we will say bye. I think, Kevin, if you want to stay online for a few more minutes, I'll stay online. Anybody else, we'll open up to just open questions. People can chat, raise their hand. Anybody wants to make comments. And then for people who have to leave and have other things to do, we will see you on Thursday.
Thanks, everyone.
So the floor is open to questions.